Today I'm going to reveal the optimizations I've been making whilst porting Sonic the Hedgehog to the Amiga. All of these optimizations focus on performance, especially rendering, which has been the Achilles heel in bringing Sonic to the Amiga platform. In fact, to give you a breakdown of how I've spent my time in the last month, I've probably only spent a day at most implementing new gameplay functionality. The rest of my time has been spent devising devious ways to get the game running faster. Let's get straight into the details, and where better to start than with the new sprite caching engine. I'll quickly recap how sprites work in Sonic, because it is a little complicated. When you see any freely placeable object in Sonic, from enemies through to rings and Sonic himself, you can guarantee that the object is made from one or more sprites. When we look at Sonic, we can see he's typically constructed from 3 to 4 Mega Drive sprite pieces, depending on the frame we're displaying. The reason Sonic isn't just a single sprite is twofold. Firstly, Mega Drive sprites can only range from 8x8 to 32x32 pixels. This doesn't provide the flexibility to create the geometry needed. The game would look overly boxy. Secondly, it's a memory and file size optimization. By piecing together each frame of Sonic from multiple components, each component can be reused between frames rather than duplicated. Remember, this entire game fits into a 512K ROM on the Mega Drive. So, the Sonic character is an object with multiple frames. An object is built from Mega Drive sprite pieces, and a sprite piece is built from multiple tiles. The object is a higher level software construct of the Sonic game engine, whereas sprites and tiles are a lower level Mega Drive hardware construct. On the Amiga, this rendering method quickly becomes a bottleneck. Imagine a situation where we have 10 objects on screen at once. This happens frequently in Sonic once you consider the number of rings placed by the designers, and even each individual moving log on this bridge I've just implemented is a separate object. As such, rendering 10 objects could easily result in 20 individual sprites, which could then require 50 new tiles to be drawn. Calling the Amiga splitter 50 times per frame is simply not practical. What's worse is that anything drawn by the Amiga splitter needs to be erased or the underlying playfield restored. So in the example I've just provided, there could be up to 100 blitter calls per frame. This is where sprite caching comes in. Sprite caching saves rendering time by storing a copy of each sprite as it is built. This includes laying out the individual tile pieces and applying operations to them like horizontally or vertically flipping tiles so that Sonic can run in multiple directions without increasing the graphics data required. With caching, drawing a sprite becomes a single blitter call as opposed to multiple operations at a per tile level. In my current setup, up to 128 individual sprites can be cached at any one time. This means that after appearing for the first time, a common object like a ring is much faster to render the second time round, and items in the cache have what is called a generation, which is effectively how old they are. Every time a sprite is used again, the generation is refreshed. This means common sprites are less likely to be evicted from the cache. You might ask, well, why not just pre-cache all the sprites? The answer is memory. The amount of memory currently allocated to pre-cache 128 sprites is around 250K. We simply wouldn't be able to pre-cache every frame needed and fit the game into 2 megabytes of chip memory. I had two choices. I could cache at a per object level or at a sprite level. I opted for the latter because it could be implemented more cleanly in the existing codebase and would be more memory efficient. But there would be performance gains by elevating the entire caching system one level up. However, you'd really need to allocate a lot more memory to the cache. Also, an object can be pretty much any size, which makes them more difficult to work with than sprite pieces, which have predictable sizes. And the caching architecture can be far more optimal if we can guarantee the rough size of what will be in it. Every sprite in the game is assigned a cache key. The key is a unique number that enables the game engine to identify the sprite. The unique number is made from the sprite's initial tile index, its dimensions, and rendering properties. Once the objects in the frame are constructed, the Amiga side of the game engine checks the 128 cache slots. If the key matches an existing entry, it's called a cache hit, and nothing much happens. It simply updates the generation of the entry to say, "Hey, I've seen you again." If a match isn't found, known as a cache miss, the cache is either searched for a free slot or the oldest entry is evicted and replaced with a new one. This is the slowest path because the entire sprite is reconstructed from 8x8 tile data, with lookup tables being used to apply mirroring. But now, it happens once in a blue moon as opposed to many hundreds of times a second for a common sprite. There is a further optimization when it comes to identifying what's already in the cache. Rather than searching through all 128 cache slots each time round, we can divide the cache into multiple buckets. Let's say we have 4 buckets. This means we need to search, at worst, 32 entries as opposed to 128. We can use a hashing algorithm to identify which bucket a particular cache key resides in. The second major architectural change involved redesigning how the playfield was restored once a sprite had been rendered. Rendering a sprite or blitter object on the Amiga trashes the underlying playfield. When the sprite moves or animates, we need to restore a perfect copy of what was under the sprite beforehand to avoid permanently imprinting the sprite onto the background. Manually copying this underlying area, storing it somewhere, blitting the sprite data, and then finally copying back the original data would add considerable overhead. The trick with all of this work is to absolutely minimize the amount of data we need to copy around, construct and manipulate. Every operation accumulates and sucks performance out of the engine. Now, as a lucky side effect of how scrolling is implemented, I always have a perfect copy of the underlying playfield in memory. This immediately eliminates the need to make a backup of that area. I have this data pre-built. Now, if you remember, an object is made of multiple sprite pieces. We render those sprite pieces individually as it seemed the best trade-off in terms of architecture for the cache we implemented. However, to restore the area under an object, why would we need to work at a sprite-based level? This would dramatically increase the number of blitter calls to copy the restoration data that already exists. My plan was to create a larger, all-encompassing bounding box around the object and use this instead. This would fold multiple individual blitter operations into one simple copy. I quickly ran into some unexpected challenges trying this out, and I think it's useful to explain what these were to highlight that something that sounds simple in practice can often be more complex than expected. Internally, in the Sonic engine, objects have a width and a height property. I thought I'd be able to use these to determine the size of the bounding box, but not so fast. These lengths are actually really used by the underlying physics and collision code. They don't strictly adhere to what you see on screen. Typically, collision boxes in games are going to be forgiving and provide a margin of error to ensure the game feels fair. Well, unless you do want a pixel perfect Flappy Bird style of cruelty. So the true width and height of an object surprisingly don't exist anywhere. We could calculate it by evaluating the coordinates and individual width and height of every sprite piece that comprises an object, but that would be slow. Instead, the solution is to extend the data format used for objects and pre-calculate this information with a quick script. This becomes a header that can be quickly read for every object. Then, at the end of Sonic's code to construct an object, we can easily build a list of every object that's on screen and restore its underlying area. I tried 2 other rendering experiments. I customized Sonic LVL, the level editor, so that I could assign 2 new properties to level objects. The first property is a way of declaring that an object doesn't need to be drawn with transparency. This was intended to be allocated to objects that don't overlap the foreground. If an object doesn't have transparency, rendering it is up to twice as fast. We don't need the extra mask layer for the blitter. But what I initially forgot was that when an object is rendered using the Amiga's blitter, for example a ring that is 16 pixels wide, the blitter actually renders a much wider area than the object itself. This isn't just due to artistic padding around the graphic, it's a result of how the blitter internally shifts data to scroll items on the screen on a per pixel basis. And the blitter itself adds or needs considerable padding on the right hand side of the image to rotate data into. Without the transparent mask, which is part of the optimization, this wide area becomes destructive and often obliterates the nearby foreground area, even when the object doesn't visually render on top of it. The optimization still has its uses, but it's more limited than I originally envisaged. One of the reasons I implemented such a boring selection of level objects, like the purple rock, rather than something exciting like a bitey fish, was there's one major optimization remaining that I really want to try. Right now, Sonic has a number of static objects that are effectively scenery. They don't animate, nor do they move. As such, it seems highly wasteful to be redrawing and erasing them every single frame. I can also tag these objects in the level editor to denote that they are static. What I need to do next is ensure they get treated in a similar manner to tile rendering and draw them in 16 pixel strips when they first scroll onto the screen. In this way, they can piggyback on much of the existing rendering optimizations used for tiles and bypass the slower but more flexible sprite codebase. Again, it sounds simple but proves more complex in practice, and this is what I'm currently scratching my head over. Once that's complete, it will mark the final major architectural optimization I can think of. We'll have a clearer understanding of how fast or slow the game can run without culling anything major. We can then plan from there in terms of the vanilla A1200 feature set versus anything cosmetic that needs to be bounced into a fast RAM version. Ideally, I'd love to get a playable demo of the first level released in August, and from that point the other levels should follow relatively quickly, but let's see how I get on. In the meantime, follow Patreon for regular updates. I try to post a couple of times a month, and almost all posts are completely free. So thanks for your support, and I'll see you next time.